Are you set up on Zoom?
I have not started the game yet. I wasn't sure. Oh, yeah.
Cool. Someone's trying to Zoom. So. Well, I'm gonna let this.
All right.
Wow. I gotta feel bad for Skype. I forgot. I mean, they were, if you want to call someone online, it was Skype call.
Yeah.
The word was that
Oh, really?
and somehow I'm like, wait, you guys aren't using what's Zoom? Where did
Yeah.
this come from? It's like, well, we're using Zoom calls.
Yeah, they definitely capitalized on the coronavirus.
I wrote it.
So, I mean, I can't fault them. It was a good business strategy, but. Yeah. I mean, I still use Skype for some people, so.
Yeah, I mean, it's got some roots, but it's just sort of the industry standard. And then Zoom happened, and you're like, what?
Yeah.
You can see there was a comment too, like the CEO.
Yeah.
He could say, we were the thing. We were synonymous with the action. We were there.
Hey everyone, it's 1:30. We're gonna get started. The classmate Caleb, as you know, he's studying to be a math professor. I'd like to have my job to my name. so he has asked if he could do some practice lectures here. So while the rest of us were taking a big break over fall break, he was studying up on these next two sections so that he's going to do his plan. Our plan is for him to speak today and tomorrow on double integration and polar coordinates, I think, next time. Yes.
You mean today and Friday?
Yeah, today and Friday is what I mean. Whatever I said, I did not mean. Okay, so if you can all give your respect and attention, and we'll get started.
So I guess I'll start with the greater paragraph thing. Start things right. Heavenly Father, thank you so much once again for this opportunity to teach with these wonderful students. I pray that you help me communicate clearly today. Some of these things are a bit more difficult to understand, but you help us accomplish all these things. I pray that we would also just enjoy fellowshipping, studying the creation. It's so marvelous that you have for us. In Jesus' name, amen. So today is Wednesday. We're going to talk about double integrals for the rest of this week. And so we're going to do that through the lens of what you already know in Calculus 1, because honestly, in terms of like the mechanical side of things, you're really not learning any new skills. So antiderivatives aren't going to suddenly change behavior. You're still going to know how to take antiderivatives. You're going to still use those in integrals. And we're going to talk about how you can apply your Calc 1 knowledge and then just expand it into 3 dimensions. And it's not really that big of a deal. So that's why the first slide is just, this is Calculus 1. This should be incredibly familiar. If this isn't familiar, you might want to go back and review the Calculus 1 integrals. Essentially, you have some curve and we interpret the integral to be some sort of an area. And so this stuff is really important conceptually, is because this is Calculus 1. So this is, you already know this, okay? And what we're doing is we're saying if we take a definite integral from a to b of a function, instead of just having that be the end all, we're now going to call this a. Okay, it's going to be some a of x. Now we're calling this integral a definite integral. We're calling it some a because what we can do then in calculus 3 when we're expanding things, we're really just doing another definite integral. So if you think about that, we're not actually doing anything super special. We're just taking that a and now we're integrating it in terms of y instead of x. And so that's where we introduce the notation. You're going to see lots of that. Where you take two integral bars, so c to d and then substituting what we had for A, and then A to be of F. And so there's a reason why I put just F into the integrand. It's because that is now a function, that's a general function in terms of two variables. So that's X and Y. And so that's why A of X actually will probably in those cases when you do problems have Y terms involved in it. And then that's why you're then allowed to then integrate with respect to Y. So we just did a bunch of partial derivatives, right? So the main conceptual basis was that when you take a partial derivative with respect to like say X, what do we do with the Y's? What do we do with that when we solve a derivative like that? Exactly. Do you think that concept's going to be any different when we do integrations?
No.
Exactly. So when we have, that's why the order of these differentials, you might have disregarded these as completely pointless in Calc 1 because there was no need to distinguish, is it going to be some dx or is it going to be some dy, right? You just slapped on whatever variable you needed. In this case, can you see maybe why it's incredibly important that dx is inside the dy? Because that comes from here. So if these were flipped, the variable that we're assuming is the changing variable actually is influenced by that order, okay? So a lot of times, one of the most common mistakes for double integrations is that it's just a little bit of sloppiness. We forget, oh, this is actually the y variable side. We need to be paying attention to this, or this is the x variable side. We need to treat it like that, okay? So a lot of it's just having neat paperwork when you do your solutions so that you can keep track of everything. So I figure, I've seen plenty of lunches happen in this classroom. I figure, all right, well, the class of a bunch of guys in the afternoon, let's do some bread to learn some double integrals today. So pay attention to what's on the slide. You can imagine we have some surface, and the top of this, the top of the bread is kind of like the function, right? It's a surface in R3 floating above the XY plane. And so what you do is when you have your piece of bread, it's like the surface is up here. And if we think about this direction being X, right, you can have some A to some B, and then you take the definite integral equals a slice of bread, right? So that's really great. You get one slice of bread. And what I've done is I basically said, all right, well, the area, you just take a normal calculus 1 related integral. Now notice though, there is a difference. We're saying that this is going to eventually be in with respect to two variables because it's in X and it's in Y. So if the area is a slice, then the volume is the loaf. And I had way too much fun using Microsoft Paint last night, Googling pictures off the internet of loaf of bread to try to find something that would work. But as if you can imagine, the whole concept of integration that you learned like way back in Calc 1, we started with Riemann sums. That's how they warmed you up into this idea of then taking an infinite sum of things. We can do Riemann sums, but with slices of bread. So here's one slice. And then if we want to add another one, we can stick it next to it. And then we can add another one and we stick it next to it. And we can sum over some finite distance in the y direction. So if x was the way we integrated this way for a single slice, then perpendicular to that's just going to be y. And so now we're going from C to D in the y direction after we integrated from A to B in the x direction. That gives us some loaf of bread. And a loaf, of course, is a volume. One thing that's really interesting is that since we're talking about actual physical spaces with a double integration, think of it as a volume. The more you think of it as a volume, conceptually, you'll set up problems easier. You'll be able to visualize what's going on in the inputs and what's going to be your parameters a lot easier. If you always remember, fundamentally, with all that, it's easy to get distracted when you don't have a concrete example with curves, but just remember, this is an actual surface. You can imagine being a physical object in R3, and it's going to be a literal volume in space. Yeah.
This question might be a little premature, but so I'm looking at this and we're talking about volume, and that made me shoot back to calculus 2 when we did volume using like the shell method and the this method. Does that mean like in calculus 3, would we never have to do that again because we're finding volume through this equation, or would we have to then incorporate both?
Well, that's actually a really good question. And I spent some time thinking about that because I had the same thought. I was like, wait a second, why do we need to do this in volumes if we already have rotational, solids? This is going to be more powerful of a tool. So this is like the more general case. When you were in calculus 2, think of the objects that you were restricted to. You were only restricted to rotational ones. So something that had some radial element that you were rotating either around the X or the Y. So that was lots of things that were like cones or bowls or donuts or things like that. But you couldn't get some three-dimensional object that was more rectangular because that's not related to like a circular rotation.
Right.
But keep that in thought actually, because when we talk about polar, there is a funny way that you can kind of solve these problems in several ways. Most times there's not just one right way to do it. Just whatever, when you're the problem solver and you're given a problem, do whatever you know how to do. And so long as it's correct mathematically and you're not breaking any rules or you're not, ignoring some very important factor you need to take account of, it should be fine. The whole purpose of this chapter, honestly, is just providing more solutions to add to your toolbox. So the more tools you have, you can solve more different kinds of problems because you have more options available. But hopefully, does that make sense?
Yeah.
Okay, sweet. So the most basic case of a double integral is when, once again, you think about it in the R2 plane, that's kind of like the input zone, and then the surface is floating up here. If you take that in the R plane, sorry, let's say R plane, R2, you actually have to bound a region that you're integrating over, right? So much how in the definite integral, with just in Calc 1, we said from A to B. What we're literally saying is we're bounding values of X. So X starts here, and then X goes to a certain point, and then we stop. That you can think of it as an area, but it's like this linear area. We literally have an area that we have to restrict a definite integral in R3. Because otherwise, we don't know when to stop. Like how much under the surface are we actually caring about to sum up boxes? And so here, we're going to talk about some of the theory. And this is going to lead us to the formulas that essentially remain the same throughout the entire chapter. They're just used in different applications. So there's a lot of funny notation. These asterisks, that just means some point within a partition. So you'll notice there's this kind of there's these arbitrary, we've cut up a rectangular region and an arbitrary amount of these rectangles. And these rectangles have a dimension where it's some change, small change in X, some small change in Y, and then inside of each of these, we need to select a point because we need to evaluate that point to then pop into the third dimension and then get like this approximating box. So who here remembers the Riemann sums from Calc 1? Right, so does this make sense in terms of the analog, how with calculus 1, we did left, middle, and right-hand Riemann sums. When you're dealing with a partition that's literally a two-dimensional rectangle, there's a lot of different choices. So we just choose an arbitrary point inside of that because these partitions that are in reality are going to get really, really small. They're going to approach this infinitely small thing. So it doesn't really matter. The precision is going to approach the volume under the surface. And so that's what you're going to say. The volume, literally from high school geometry, it's an area times the height. Okay, so do we all remember that? If you can remember that in general intuition, setting up these sums and these integrals, it's a little bit more straightforward. It's really just a volume. You take the function evaluated at some point within your little partition, it's going to give you the height of your box. So multiply height by area, you get the volume of one of those boxes that approximates a certain partition under the curve. And so just to understand these partitions a little better, because I don't know about you, I was super confused last week trying to figure this out on my own. So if this is just, we're taking a look at one partition, and one of these rectangular partitions. Once again, we have, what the sub K means is we have an arbitrary number of these because we're allowed to split up the region in R2 in any number of ways that we want to, so long as we're using rectangular partitions. So with the sub K, it doesn't have any special meaning. All it means is we had to choose a certain partition. This is the case partition out of 1 through n partitions. And then we change in X, we change in Y. So by high school geometry, the area of our little partition here is just the product of those two, right? It's just length times width. And then we have a point. once again, this is a completely arbitrarily chosen point. The only condition for this point is it's got to be inside of the partition, because that's what we're going to use to plug into the function to approximate the height of the box. And then we get a volume by doing height times area. Height times area. It's going to be essentially just repeated over and over and over again in a bunch of different contexts. Volume, one box partition, is the function value multiplied by the area of the partition. So we can approximate the double integral with just a sum of those boxes, right? So if you tell yourself, okay, I've cut up my rectangular region into so many partitions, and I'm able to now approximate essentially all these little boxes underneath the surface, then I just sum them up. I'm going to get this kind of really rough pixelated approximation of what the true, volume under the surface is going to be. And so that's what we represent with this sigma from the first partition, so k + 1, up until however many partitions we chose to do, which is n. So naturally, this is calculus. We are worrying about what happens at the infinite extremes of things. And this is when this is a symbol. We use this delta in the context of the diagonal of that rectangular partition. And essentially, all it is, that's going to approach 0. In other words, we're going to get infinitely more and more and more precise. We're going to get infinitely more and more boxes that we actually have to sum up. And that's going to result in there being the actual volume underneath. And so this is a slightly new notation, by the way. It's a little bit different than that very original just double integral with, it looked like two definite integrals. This kind of looks like they're just smashed together. But this R, when we sub R, it's the same idea of you have a double integral, which is a volume, and you have to say which region you're actually caring about for that volume. So does this limit make sense? Like how we're summing up these boxes and then it approaches 0, gets infinitely precise. It's the same exact logic from calculus 1, just up to 1 dimension. So are we all good? So let's derive our rule. I'll have a little fun with you guys because the textbook does this in a really boring way. They give you the formula and then they move on. So you're going to learn why you can actually use this. And this is important because this is the rule that says you don't have to learn any new techniques. You can use all of your integration techniques, all of your integration knowledge from Calc 1, and just apply it twice in Calc 3. So what we're going to do is, if you imagine a definite integral from A to B, you want to split that up into an arbitrary number of partitions. That's all that means. So x0, x1, yada, 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 and you have n arbitrary partitions in between. You do the same exact thing in the y direction now, because instead of just going in one direction, we can now sum up in the y direction as well. So we cut that up into an arbitrary number of pieces. We can have another rectangle, and this rectangle is going to have dimensions essentially at the start of one partition to the next, and then the start of one to the next. It's just another rectangle, such that then basically this difference is the length. Once again, this is a callback to this simple image right here. This is really, really motivating kind of everything in this little proof. So if we have this rectangle, we can say that the change in the x, the change in the y. Now, what is this? These are fancy terms essentially for a minimum and a maximum. So INF stands for infimum. It's something you don't really need to know at all for this class. It's essentially just the smallest element of a set that is less than or equal to everything else. In other words, minimum, but now that's a minimum for truly any dimensions. And then the capital M is supremum. It's just the same exact idea, but it's the ceiling kind of idea. And so, I mean, not many people like to retain every single rule that they learn from their calculus classes, but who remembers the comparison property of integrals from calculus 1? This is way back, this is a callback. Essentially, you can take the minimum and you multiply by the difference of the area of the region that you're kind of integrating in. And that's like saying that's the bounding lower area. It's going to be, that area is always going to be lower than the true integral. And then the max takes the highest point of the function. And it says, okay, well, now this is the maximum area. So its area is going to exceed that of the true value of the function or of the area of that curve. And so we can bound this integral below and above. And so all we really got to do is just apply it in 3 dimensions. It looks a little bit not as visually pleasing, but it's the same exact logic as calculus 1. It's just applied twice. It's a copy and paste of logic. So this top step, minimum, that minimum idea, times the change. There is no difference between this step and just calculus 1 step, because this difference is a delta, and that delta x right here. So we do it in x first. We take the minimum multiplied by the change, and then here's our integral. So that's the true area in terms of x. And then we cap it off with the maximum area. And then that little condition at the end is only the caveat because we're in 3 dimensions now. So we have to make sure we're talking about the y values inside of our partition. We can't just choose random y values, right? They've got to be within our partition that we're talking about. And then all we do is we sum up all the partitions to get this sum. And then notice that that allows us to make a statement about this definite integral. Now we're looking at something a lot more familiar. Okay, we're able to bound our definite integral that looks a lot more familiar and not intimidating and scary with these 2 sums of all of these partitions. We can actually just copy and paste this idea again with that comparison property of integrals by taking whatever this gross thing is, which is really just an area. Area multiplied by a height is a volume. So volume, true volume, maximum volume. So maximum volume is going to contain the true volume, and the true volume is going to be greater than the minimum volume. So we're just smashing the volume in and making it, squeezing it in to find what it is. Once again, all we do is sum these things up, and now look at that. That is kind of what we're aiming for. There is our comfortable double kind of definite. We call this an iterated integral. When we iterate, essentially what it means, iterate an integration. Notice the order of these differentials. Okay. In case we started by going in terms of x first, and then we went in terms of y. But no, we could have done that with y first, and then gone in terms of x. And so this is a really powerful observation that's going to give us something called Fubini's theorem. So we recognize if the minimum for all the sizes of partitions, that's a really powerful statement, because that means a partition that is infinitely small, it's still true. So if you can squeeze this thing to be infinitely precise, below and above, then they must be equal to each other. So that's why we can show that double integrals can really just be represented and solved for mechanically like an iterated integral. And so long as that your function is integrable for both x and y. So now, if you see something that's written in terms of this, you need to double check that the function is integrable in terms of x and in terms of y. And if so, you don't need to do anything special. You just need to use your calculus 1 knowledge and apply it twice with this iterated integral. Yeah.
Can you explain one more time the difference between an iterated integral and a double?
Oh, gotcha. Okay. So the double integral you can think of as the highest level of abstraction right now. That's just any volume under any region under any function. So that's what this guy is. Because it's any area for any region R for any function, and then that dA is now because you're talking about an area. Where the iterated integral says, okay, hold up, we can dissect this. So practically speaking, what does that mean for us? That means we can just take the first integral in terms of x, just like we would normally do in Calc 1, and then we take whatever result we get from that, and then we evaluate it, stick that in the integrand, and do it again for y.
So could you also, from the double integral, wouldn't there be a second iterated integral that also does equal to that?
Yes, that's exactly what the theorem states. So in your textbook, this is the Fubini's theorem of equality of the double and iterated integrals. That was a really good observation, because this is really powerful because you can actually flip-flop the order of these things, so long as the conditions are met. This doesn't, like, the way the text kind of presents it is just, here's rule, now use it, without really explaining. This is super powerful because sometimes you'll run into a function where it's incredibly difficult to integrate with respect to, say, x first. But If you were to do y first, now it's a piece of cake and then you can proceed forward. So this is more of just a practical problem solving theorem that we could use to simplify problems that would otherwise be really difficult. Yeah, Quadrin?
So kind of, as you were saying that, something hit me where it's like, okay, so you know how like when we just did partial derivatives, you could do it x twice. Would there ever be a circumstance in which it would be dx instead of doing like dy and dx?
That's a really interesting question. I guess think about that geometrically for a second. So suppose you were to actually integrate something in terms of x. Actually, let me use one of the old pictures here to try to illustrate this. So if we were to take this, right? We're integrating with respect to x for a function. That's going to give us an area. Now, if you were to try to integrate that again with respect to x, that's not really necessarily what you would use for a definite integral, because how would you take this slice and iterate it along, sum up a bunch of those pieces continually in the x direction again? So if I were to be completely honest, I do not know. But you can look at, if you find something, let me know. What I can tell you is that in terms of indefinite integrals, we're on the fundamental theorem of calculus side, where we only care about kind of the direct relationship between derivative goes this way, integral reverses it. Then taking an integral again with respect to x is just like taking 2 steps back in terms of differentiation instead of taking a derivative twice. So does that make sense?
I think so.
We have to see it in terms of, well, y'all are engineers. This is perfect. Physics. What if you take the integral of acceleration with respect to t, get back to velocity? If you were to do it again, you get back to position.
Right.
So you can do it that way because it's a family of functions, but those are indefinite integrals. Geometrically, in terms of like actual solids or areas and volumes, I don't think there's a practical kind of application of that, unless, is there something, Dr. Hart, I'm missing? Okay.
Okay.
No, you don't do, in a way, X and Y are the same. So you could do it, if you had symmetry, if you had some kind of symmetry where it turns out that the Y and X are equal in some way, then it is, but there's nothing that's, we don't ever talk about like the double interval. We would rename it Y even if it was the same.
Got it. That makes sense, actually.
But I do like your question because it does show that in this particular theorem though, it's not kind of like how you could take partial with respect to x and then with y, and that mixed partial is equal to if you had done f with y first and then with x, so long as functions meet those conditions of being continuous and we're defined. This is the same exact thing. We're just going the other direction now. So you can integrate the x stuff first, assuming x is varying, and then with y. And then you're going to get the same exact area as if you had started with y changing and x. So you see how it's a little bit analog? It's just not 100% identical, but it's very similar in concept. Yes.
Okay, so with our points A, B, C, D. So if we're in 2 dimensions, right, we have points A and B that we're integrating from. So if we're in 3 dimensions, does that mean that all 3 of these values be like, if you have like a solid, right, is it going to be like A, B, C, D on the same plane? Like, like down, like how you want to define this again?
I see what you're asking. Everybody take out a piece of paper. Okay, and draw a rectangle. Just, I don't care what kind of rectangle, just a rectangle on the paper. Okay, so along the horizontal, have A be the left side, and then B is the right side of that rectangle. And then in terms of Y now, let C be the lower corner, and then D is the upper. That's what those bounds mean. It's saying you can go in those horizontal directions in your input area without extending up into the actual function region, if that makes sense. So does that clarify, or is that still? Okay.
So he's saying that this is like our or the same way like T say D. You just had you only work with this for a 3 dimension, right? And then so you could change any this stuff is changed will be changed. And that would affect your volume. That makes sense. Where the same way if we affect this line, your area is gonna be either heightened, shortened, it's not.
Right. So if you heard what Quadre said, he's very correct. That's a good way to kind of conceptualize and kind of process what's going on here.
Can
So-
I make a comment?
Yeah.
In Calc 1, you're integrating over line segments. In Calc 2, we're integrating over, in this section, over rectangles or over regions. So today, when we're doing rectangles, it's a line segment going this way, no, it's a line segment going that way, which together gives you the whole box.
So is A and B on the x-axis?
Yes,
C and D is on the
conventional.
y-axis?
Yeah.
Okay.
And once again, think about what a variable is. I mean, ultimately, a squiggle of, ink is completely meaningless until we assign arbitrary meaning to it. So conventionally, we say A to B because that's kind of like what we did in calculus 1. So we're still familiar with that. So we associate those variable names at least with the x direction, and then CD with the y direction. So anyways, let's do some maths now.
Really quick, you should be good. They extended your time limit on this,
Oh, thank you.
so I'm ahead up.
Can we give my brother a hand? He's helping me record the Zoom today, and it's his birthday.
Your backpack open?
Yeah, just are you aware that your backpack's open?
Yeah.
Okay, good. Don't worry, you're gonna be fine. So I know you guys love the part when I ask somebody to come up and then try to solve a problem. So who wants to solve? And we're all gonna solve this problem together. So who wants to come up and be the scribe for the class?
I don't.
All right, Quadre. Okay, so for the rest of you guys, in the meantime, let's start to think about what a lot of times problem is quote hard because we're simply kind of just too lazy to like literally see what it's asking from us, right? Most of the times, a problem that has a solution gives you the things you need to solve it, right? So let's take a look at what we're given here. So go ahead, you could start brainstorming, but these are the bounds. So sometimes the notation is just a stupid obstacle conceptually. So what's really going on is here's our x, and it's going from 0 to 1. So this is really just A, B is 0, 1 for our x's, right? Okay, so then for you guys, what does that mean for CD? Right. So let's keep this down.
Well, I'm just setting.
Oh, yeah.
So if we keep looking up
It's
there.
totally fine. And so now, before he gets to the iteration, what do you think is going to be easier to do first? Assuming x is the variable, or assuming y is the variable? Right. If you have to do y, now you have a product in your integrand. You have to do integration by parts. It's time consuming. It's obnoxious. Not that it can't be done, but why do it if you could save time with x? Yeah.
So you mean the way this matter was used?
Right, because if you think about it, these functions, they're continuous, they're defined everywhere, they're well behaved, right? They're smooth. So by the theorem, you could go either way. And if you did do the work, you could show at the end of the day, you're going to get the same exact answer. But I mean, knowing the engineering creed of get the answer as fast as possible, we want to take it as easy of a route as is possible. So let's see.
So I do something like this, where I separate the y from, if I'm integrating for x first, when I separate the y like you would like a constant, you just
Well,
have to integrate.
You don't necessarily have to separate it. You just think about it conceptually as a constant. So guys, help them out. So if you have y, e to the xy is the integrand. We're just doing an anti-differentiation where y is a constant. So think about what would you take the derivative of that would get you to here, assuming y isn't changing. It's just like
Oh, so you would just take the derivative of e to the x, y, which if you take the derivative of that,
the
y
chain will
is-
throw that constant.
yeah, exactly.
So your new integrand actually doesn't have a y down there. It's just e to the xy. So go ahead and write down the derivative. Here's what to do. X,
Oh, Okay, my mind is still in derivative. I'm like, when I have y squared, I'm like, because I'm not thinking the integral fraction divided. Gotcha.
So what's that going? What's that going?
Should I build off this or stay over here?
You can write it down so that they know what's going on.
You would have y e to x y.
And lo and behold, that looks a little bit familiar, right?
Right.
That's the integrand, which means this is the antiderivative. So now that is what we're going to evaluate for that first definite integral.
Gotcha. Which,
And then
that
This
would
is,
end up being
this
one.
is correct, but just as a small notational note, you don't want to leave your poor y hanging. Because you'll eventually cover him at the very end of when you
I have a bad habit of doing that. Which, 1 times 0 is 0, so e to the, oh, wait, no, that should just be, I'm leaving the y line. So if I integrate with 1 first, I would have just e to the y.
Mhm.
So, and then, so it would be e to the y minus, e to the 0, which is just
Which
1.
is just gonna end up
So I just
being
have. So I would have the integration 0 e to the y minus 1.
Mhm. And then now you have the differential y. Now look at that. So things kind of work out. And then that's just a calculus 1 integral that you can evaluate.
And at that point, I would just,
Do that whatever you would
Again.
think. Yeah.
which.
So if y is the variable now.
So would it end up becoming e to the y minus y?
Exactly. And then you evaluate that antiderivative with the new definite integral bounds. And then by the time you get to this step, you've essentially done all the calculus, right?
Right.
That's all the calculus stuff. The rest is, you plug in chunks, you simplify a little bit of algebra.
That's
And
not too bad.
no. And then what you do end up in case you're wondering, like if you essentially plug in the natural log 2 minus natural log 2 minus 1 to get 2 minus 1 is 1, and then you still have the natural log left over. So that's all there is really to the simplification of this. Yeah.
Okay.
So
That actually
next-
helps. I would recommend if he does another one that people, you should volunteer. 'Cause now I get it's clear what's going on.
Thank you so much. It's okay. I mean, we're gonna do another problem here, but. Okay, real quick, I don't want to spend too much time on this because this is, you don't really learn anything new. There was average value concept from calculus 1. Essentially, you take 1 over b minus a, which is that, like she's saying, the line segment that you integrate over, and you just multiply that by whatever integral you got. The same exact idea happens once again, except for now, once again, it's a region with an area. So just take the area of R, and that's what you stick in reciprocate. Multiply it by whatever the double integral is. So does that make sense? There's not really anything. You can essentially derive this formula by just remembering what happens in calculus 1. And so actually, speaking of doing another problem, I remember sticking the problem in the note. So I need another volunteer for this problem. All right, let's go. What else?
I think we did a little bit longer.
And actually, when you guys are not up here volunteering, that means you're actually probably gonna do a little bit more work than him. because you're gonna be solving it in your notebooks right now. And then you're gonna be checking his work, because he's gonna say, hey guys, does this look right?
Don't say no.
Those eyes. Look at me. I feel like he's got the eye of Sauron. It's like,
So, and actually, what I'm gonna do is I'm gonna go sit down. You're gonna teach us how to solve this problem.
yeah, David.
Okay, so I'm a teacher today, you all get Fs. But so we're gonna start out just doing the double integral, setting up A, B, and C are both 0, 2, I believe, which my handwriting is terrible, but that's what that means, I promise. And just going to put the F of X in. Excuse my handwriting, for lack of room. So with the first one, which treating each of those as, well, y as a constant to start out. Y, X. Do that from 0, you should get 0, and then the whole thing. Equal 2. Then you can put that back into the second integral for y.
Oh wait, hold on. Did you you lost your y somewhere in the mix?
Yeah.
Because remember, so when we substitute, in the x, y is still a constant. So we just kind of put those definite integral, So it'd be 2 minus 2y. Yes.
Don't forget that part, it's important, guys.
I was like, wait, you're just gonna get a 0 anyway.
Yeah. So that one integrated with respect to y will come up to 2, which is y minus y squared, which is from 2, which comes up to 4 minus 0, 4, 0. I think. Yay.
And so you got lucky because the integral ended up being 0, but if it's the average value,
Oh, it's one of the.
We find the
you would want to be able to just know how to take that, find the area of R. In this case, it's a square.
It's a 0 length of 2.
So will that be
2,
1 over
so
4?
1/4 of 0.
Right. So you have the area of R, which is 4, so 1/4. This double integral. Was that a stretch? Awesome, thanks. By the way, thank you, David. He basically just nailed that on the What?
Sure, you get the A.
So I have a question. So in this case, it was a square, right?
Yes.
So that's why we ended up multiplying 2 times 2, and that would be 1/4, right? If would we be getting like a circle or something?
That's an excellent question. Because yes, that's essentially what we're going to be talking about now for the rest of the sections, is that region in R doesn't have to be a boring rectangle, as this region can be literally anything, right?
Yeah.
And so actually, it's almost like I paid you to ask that question at the end of the example, because this is precisely where we step into, right? Now we can talk about a double integral over any region R. And so you will want to be able to understand, it's not, don't just assume you're gonna get like a rectangle that you can get your area. So this can now be anything. So long as it's under where obviously the function is continuously defined and stuff like that. But you'll notice that when you take the sum once again, nothing really changes symbolically. Although conceptually, you kind of want to think about it slightly different, but these partitions aren't going to be necessarily those rectangular partitions over a rectangle. So the proof gets hairy, and I didn't understand it in terms of the arbitrary side, but the limit is still exactly the same. Why? Because we only care about when these things get really tiny, and when those partitions get really small, all of this notation kind of falls into place, and that's how we're defining this double integral. So there are different combinations that this region could be. So like Marco, you were asking, is it always going to be a rectangle, or what are we going to always have? Well, here are some examples of ways you could bound that area, right? You have two kind of constraint curves inside of like the input area where we're restricting where we're integrating, some G and some H, they can be kind of paired up in these different ways. You can have it where it's just hanging from A to some B, or like they have an intersection at your A, but then they don't have an intersection at B, or of course, they might just actually have intersections on two sides, and then you only care about kind of what's in between and where those intersect. So essentially, it's really kind of important to establish your visual. I know you guys in engineering, you like diagrams, you like pictures, shows you what's going on. This shows you exactly what's going on. In terms of the X, when you integrate perpendicular to the X, so when you integrate with respect to Y, you're gonna get some area, some A of X underneath the curve. We take whatever that is, and then we integrate it now in terms of X in this particular diagram. But notice that what we're actually limiting in terms of Y, what we're limiting that area is actually now changing. So the limits of integration are changing as functions as you integrate those areas. So those areas now are actually non-constant, or you can't assume them to be constant. And so I'm going to walk you through an example first, and then there's going to be one more problem that we might have time to get to. So you have the integral, double integral for 2x squared y dA. That's an iterated integral. So R is now bounded not by just a rectangle, we're bounding it with actual curves, with functions, okay? And so in this case, we just have two parabolas. One of them opens up, one of them opens down. So the first thing you should do in this case is not start trying to integrate because you don't know what you're doing. You have to know where your region is in the plane. Got to know what you're allowed to do, how they're related to each other, so you understand which direction am I going to go first, and how far do I need to actually be summing things up. So let's graph these parabolas. And what you get is the red one is obviously opening up. So that's 3x squared. The blue one is 16 minus x squared. So notice there are a few important little pieces of information. For example, like on this interval from -2 to 2, that's where they're intersecting, right? So those in terms of the x side of things, when we're concerned about that, what do you think the x limits of integration are going to be? Based off of the intersection points in the curve. Right, exactly.
0 to 16.
Now, I like the way you're thinking. You're going bottom to top, but notice that that would only be true at x equals 0. We're going to be integrating a bunch of areas that are going to be changing. So what's changing is now the limits of integration in the y direction. So it's really g, or the 3x squared, to whatever 16 minus x squared is. So you're allowed to use a function as a limit of integration when the region is like changing with respect to functions.
So like we're inputting a, oh, okay, it's exactly what you're saying.
Yes, it's literally, quite literally, you're allowed to do that. You take an area where it's the bottom bound is whatever the function ends up being, and then it's capped off by whatever function's on top. Now, this order you might notice is kind of like really super important, right? Because graphically, you get something nonsensical if you try to go the other direction. You're going to be going the wrong way. Since the blue curve, since this the closed parabola is on top, and you're going to integrate from bottom to top in terms of the direction, then you need to identify and graph these things to know which one's going to bound on the bottom, which one's going to bound it on the top. And so that's why when you're doing a practice problem, you're like, oh my gosh, well, wait, hold up. Which function is going to be my lower limit of integration? Which function is going to be my upper? Chances are, just graph it, get your bearings of what that region is supposed to look like in it all. You can just use your eyes and see which one's lower, which one's higher. So we already found where the curves intersect. That was just, you can eyeball it. You won't always be able to eyeball it. Yeah.
I just had a quick question. Can you explain why, when you're going from left to right, you can just use the points -2 and 2, even though those are normal lines, you know, those are just lines. But when you're going bottom to top, you have to use the functions that all the curves.
That is a really good practical question for doing problem solving. So what we're doing is if we're defining R to be the region enclosed by both parabolas. So that's specifically going to be in between. Yeah, and I don't know if you caught that in the original problem, Stan. It could have been lost too. But it's like R is the region bounded by the problem.
Yeah.
So specifically that inside region. That's a good point. If it would have been something different, this is a completely different problem, right? If it would have said explicitly from only -2 to 0, for example, then you're only going to do that. But since they didn't give us those the bounds in the x direction, we had to find that just using some algebra. Yeah.
So for example, just to make sure I'm understanding this right, if we had this function, like let's say we inverse or whatever, and now it was like sideways, and so it was intersecting at on the y.
Oh, so you're thinking of just rotating everything
Yeah,
90
we
degrees. Yeah.
rotated it, then our y would be bounded, and we could use like the numbers we have on our y axis, but on the x, like concerning x, it would be the function in that case.
We're actually, I don't, we're probably not gonna have time to get to it today, but essentially we're gonna talk about how, yes, you can have now instead of, these are y equals g of x. So a function y in terms of x, a function y in terms of x. You can just do it with x as functions where y is now changing. So you're just gonna get like you said, a 90-degree image, but when you actually perform the math, you wanna make sure that your functions are actually defined where x is the function and y is changing. Because if you don't, you have the image flipped correctly, but then you're not doing the math as if you were. And then everything gets kind of wonked out. So does this setup make sense? Because honestly, like the setup is almost more valuable than walking through the problem, because once again, the mechanics and all of that is exactly the same as calculus would. It's like you're not learning anything new for that part. This is the only stuff that you really got to make sure you understand conceptually to set up problems. Yeah.
How did they get the 2x squared y?
Oh, sorry. That was from the original problem.
Yeah, that was the original.
So that's the surface. That's the surface that
Can
we're
you
finding.
wait
on.
for the little bit?
Sorry, what?
Can you just wait? I'm just gonna-
Which slide?
No, there.
Oh, okay. So let's see, it's 2:20. So maybe what we'll do is I'll real quickly, for your sake, I'll show you the y direction. Like, so if x is now a function in terms of y, you can work on this problem if you want, but you're gonna have plenty of homework in the Pearson as it is. So, but yeah, the same concept does apply if we're gonna bound the r in terms of now just this way. So now x is going this direction, and we go from left to right between two curves that are defined such that x is now the dependent variable to y, which is changing. So do you see the difference? Like it's completely analog in terms of like the way the equations are set up. It's just making sure you don't get yourself twisted and turned over conceptually when you're setting these up.
So for that one, you take the derivative with respect to y first, and then with respect to x.
What you would actually do is you would want to integrate between the functions first. In this case, that horizontal distance between the functions is horizontal, aka x. So the inside integral in your iterated integral will be something dx. And then you get that, because that, if you think about it, it's going to protrude, it would point directly outside of the screen, some area under the surface. And then you iterate all those areas now in the y direction afterward. So does that make sense?
And is that because you want to do the like smallest constraint last on the integrals?
I wouldn't necessarily say smallest constraint, because the words small and big are kind of arbitrary, as you can see. That would be super small because it's zero difference, but that doesn't influence the order in which we do things. The order in which you choose to integrate should be primarily motivated by how the region, it's essentially a convenience thing. So if your curves are organized in the space in such a way that when you have the literal equation, so it's no longer just theory, it's like actual applied equations. If it's easier algebraically to deal it with this way, do it this way. If it's easier to do it the other way, where y is the function and x is the variable, do it that way. There's no right or wrong here. These are all just tools telling you what you're allowed to do without breaking the math.
Your inside function, the limits will be the function in the outside, try to run numbers on the outside, so that you end up with the number of.
Okay. I guess what I was saying.
And the other thing is, you can change, it's just the inverse functions themselves, like it has x equals gy, well, if you do the inverse function, you can get y equals inverse gx. So you can, if you know how to take a function when it's inverse, then you're gonna be able to manipulate the limits for whichever variable you want to. First.
Thank you. So here's, this is essentially what Dr. Hart is saying. When you do set these up, the ones that are in terms of functions, in other words, the changing region, that's inside, because otherwise you're not going to actually get a volume. You'll probably still have a bunch of variables still left over. You don't want that. So the stuff with the constants stays on the outside. This is in the textbook. So actually this is perfect timing because I have just one more slide with the problem on it. So what we're gonna do is go ahead and copy this problem down. When we start class next time, and you bring me your solutions.
If I remember. If I remember.
Okay. And then I think what I'll do, that's the end of today's lecture portion. So that's gonna be just basically one problem. Try to get that done before Friday because it'll kind of make sure you don't forget literally everything that happened today, which happens. So, and then I'll be obviously here till 2:30 to answer questions.
Michaela, can you just take a moment and explain to the class why that last sentence is important?
Oh,
Notice
okay.
that.
So this says, notice that the function, so our function in R3 is positive for a region. So think about it like this, when you're in Calc 1, if the function dipped below the x-axis, suddenly you had to deal with like a negative area, this idea of negative area. To get a true volume, we want to ensure that the surface is actually staying above the axis. Otherwise, we're going to have to now account for, are we talking about a net volume, where we might have to subtract away some volume that was negative below the plane, or are we just keeping everything positive? So this is telling you, you don't have to worry about that. The surface is always going to be above the plane, which means that when you find this volume, it's going to be just a positive volume, whatever number you get out. So.
It's like the equivalent of saying this is where no air resistance is negative.
Kind of, right? It's a convenient condition that makes the problem solving a little bit less annoying.
Or a general question. So if we're taking double integrals, we're basically kind of like with taking the integrals. Well, with integration, you just take the sum of a bunch of rectangles, right? One here, and the curve. And in this, we're saying you're adding up a bunch of, I guess, rectangular prisms, 3D things to get the area under whatever you like a plane or a function in a 3D.
Right. I think here's a good way. This helps me conceptualize it. So the first thing that you said was the normal, like just an integral,
Right.
was just you sum up a bunch of rectangles
Right.
to get an area.
Right. Area. This is given a volume.
Now we take area and then we multiply area by some sort of distance now in another direction.
Right. So say you add a fourth axis somehow, or you get into a fourth dimension, could you still apply?
Yes, triple integration, 16.5.
Okay, you can decide that means equal.
And then those Riemann boxes are actually now cubes. And so then you have, yeah, and things get a little bit more complicated there. But
Yeah, I'm just wondering if that's what it is.
Yeah. I mean, ultimately, the concept of integration is here's something, here's bounds, sum.
Yeah, that's what.
So, yeah. No, we'll get to that. We'll talk about triple integrations next week. That's all for class content today. And then I'll assume you've got that problem written down.
Does it look rougher like that?